Hi, today I would like to discuss the paper on the Hölder continuity of the convex minorant of a Levy process. This work has been done in collaboration with Jorge Gonzalez Cazares and Alexander Mijatovic, both associated with the University of Warwick and the Alan Turing Institute. So in this picture, we consider the path of a Levy process x over the interval 0t in gray, and beneath it in the red function, we see its convex minorant. In the paper 1, we characterize in terms of the transition probabilities of x when its convex minorant C is smooth, and specifically we prove that C is Lipschitz continuous if and only if x is a finite variation. Hence, to ask the main questions of this paper, we'll restrict ourselves to infinite variation. So the main question we'd like to discuss today is the convex minorant C R Hölder continuous almost surely for some R between 0 and 1. And what we mean by this is when is the Hölder constant defined to be the supremum over all u and t between 0 and t of the increments ct minus cu are divided by t minus u to the power r. When is this constant finite almost surely? So to answer this question, we'll define a few things. So let nu be the Levy measure of x, nu bar be the tail, and Blumenthal-Couture index is defined by beta, which is the infimum of all p, such that this integral is finite. Note in this regard that this integral where we substitute in beta need not be finite, which is important for the following cases. So let's consider a Levy process with a Brownian component. So sigma squared is now positive. In this case, the result is completely characterized, and we see that the critical case is 1/2. And in this case, the critical case goes into the case of no. So larger than or equal to 1/2 and strictly less than 1, C is not R Hölder continuous, and strictly less than 1/2, it is R Hölder continuous. If we look at the simple case of sigma squared 0 and beta between 0 and 1, then for any r, it is going to be R Hölder continuous. Now, in the more interesting case where beta is strictly larger than 1 and less than or equal to 2, and this integral we discussed before is infinity, then the critical Hölder exponent is now 1 over beta, and this critical case goes into the no category as we saw before, in the sense that larger than or equal to 1 over beta is strictly less than 1. It's not R Hölder continuous, and strictly less than 1 over beta, it is R Hölder continuous. Now, if we now define the integral I beta to be the integral over the expectation of the function we see here with respect to the measure t over t, then we say that when this is finite, then the critical case now goes into the yes category instead. So less than or equal to 1 over beta, then it is R Hölder continuous, and strictly larger than 1 over beta, it's not. Right, so note in this case that these two restrictions are mutually exclusive, but they are not necessarily complementary. Okay, for example, we can see that if we assume that this thing is finite, then I beta is going to be finite. However, to go the other way, we need extra assumptions. So if we assume that this integral with beta is finite, we need the extra assumption that x nu bar of x to 1 over beta squared is finite as well to see that I beta is finite. Okay, so how do we control the Hölder constant to show that we actually have Hölder continuity? So recall that the convex minorant C is a piecewise linear function with countably many maximal intervals of linearity with horizontal lengths Ln and vertical heights Xion. Right, and we denote the set of R slopes of the convex minorant by Xion divided by Ln to the power R. Okay. So if we take the nth interval of linearity, we can note that C has slope Xion divided by Ln, and specifically we have that on any interval of linearity, C is going to be R Hölder continuous. Specifically on the nth interval of linearity, it will be R Hölder continuous with constant Xi n divided by Ln to the power R. Right. However, note as well that C might be locally R Hölder continuous on the open interval 0t, and it need not be Hölder continuous on the closed interval between 0 and t. And this is because 0 and t are not endpoints of maximal intervals of linearity, because x is of infinite variation. Okay. Now note this line of inequalities, which is going to be very useful for us. Okay, so we see the Hölder constant here, and in the lower bound, we, instead of taking supreme over all u and t, we only take supreme over the set of r slopes. So that means that we restrict ourselves to endpoints of linearity, and then we take the supremum over all such r slopes. This is clearly a lower bound, and for an upper bound, we can see that you can use Hölder's inequality for C prime and power functions to get to this upper bound, which is the sum over all r slopes to the power 1 divided by 1 minus r, all of the sum to 1 minus r. The reason why this is tractable is that because to show Hölder continuity, it's enough to show this constant is finite. Okay, so it would be enough for us to show that capital Kr is finite to show Hölder continuity. However, it will also be enough for us to show that small kr is infinity to show that it's not Hölder continuous. Okay, so our main results from this paper show that for most Levy processes, small kr and capital Kr are simultaneously finite or infinite. So that means that kr infinity intersected with small kr finite has probability 0. And this is what yields the table in 1 we saw before. Okay, so how do we prove these things? So we have this 0-1 law for unbounded functionals of the faces of C, which is proposition 1, which is going to be very useful. And we consider some phi that's measurable, and then the sum over all n of phi of the heights and lengths is either almost surely finite or almost surely infinite, and it's going to be finite if and only if the integral over the expectation of the minimum between phi and 1 with respect to the measure t over t is finite. So the proof in the case where we are away from the critical case, so that means that r is not 1 over beta and sigma squared, say, is 0, then we can use proposition 1 to characterize the finiteness of the supremum over r slopes in terms of the integral of the probability that norm of xt divided by t to the power r, strictly larger than some capital R, with respect to the t over t is finite for some r. And we can use this specific phi to get this. Then Kinson gives you a direct link that shows that this is exactly the way to characterize when lim sup of norm of xt divided by t to the power r is finite almost surely. And again, we can use now Bertrand, Doney, and Mahler to show that this can be used to characterize things in terms of nu, so the finiteness of integral of nu. Right. So this gives us specifically the finiteness of kr in terms of integrability of some function of nu. However, how do we prove that capital Kr is finite? Well, since we're not in the critical case, we can take some r prime strictly larger than r, and note that capital Kr can be written as the sum over the heights divided by the lengths to the power r, to this power, and then you can push in r prime. So we have small kr prime times this, the sum over the lengths to the power r prime minus r divided by 1 minus r, where this sum will be finite, and hence if small kr prime is finite, this will imply that capital Kr is finite. So it really pushes the problem of answering whether capital Kr is finite onto the characterization of the finiteness of small kr. Okay. So now, in the critical case where r is equal to 1 over beta, things are slightly different. In the case that in this regime, we show that this integral with nu bar t to 1 over beta is infinity if and only if small k1 over beta is infinity. almost surely, and we show that I beta is finite if and only if capital K1 over beta is finite almost surely. So how do we see this? Well, since we can write capital K1 over beta as the sum over 1 over beta slopes, we can use proposition 1 to see exactly that this happens when I beta is finite. And we can see this by choosing this phi. And to look at the finiteness of K1 over beta, so the 1 over beta slopes, supremum over these slopes, we can see that this is infinity, again, by using the same steps as we saw on the slide before. So we use proposition 1, we use Kenshin, and we use Bertrand, Donny, and Mahler to see that this can be characterized in terms of the finiteness of the integral on the right. So here are the references mentioned in the talk, and the link to the archive paper will be in the description of the video. Thank you so much for your attention.